Hello, everyone. Thank you for joining our webinar. Today's session will take approximately 1 hour. If you have any questions during the presentation, please ask them using the Q&A feature located on your Zoom toolbar at the bottom of your screen. You will be able to see questions from other attendees, so please upvote or like the questions that interest you. This will help us determine which questions to address live at the end of the session. Watch for an email tomorrow with further information and a link to the recorded presentation. And now I'd like to introduce Johannes Doerfert from Argonne National Laboratory. Johannes?
Thank you very much. Okay, let's see if this all works. Okay, so my name is Johannes Doerfert, and I work at Argonne National Laboratory in Chicago. So a little bit about me for those that haven't met me before. I got my PhD in computer science from Saarland University in Saarbrücken in Germany. Afterwards, I started as a researcher at Argonne, and I've been there ever since. And I worked in the LLVM community since 2014 and in the OpenMP community since 2018. And kind of recently, I became the official code owner for OpenMP Offloading in LLVM. So very involved in the OpenMP offloading development as part of the LLVM compiler framework, but also in OpenMP optimization, which we will talk about today, and the OpenMP front ends, the OpenMP runtimes, everything that kind of connects there. Okay, so let's start with a little bit of background. LLVM in a nutshell. Given that this is supposed to be a compiler talk, I'll try not to actually show LLVM IR or anything else, but you need to know a little bit about it, or which is generally the same for all compilers. So what I'm going to tell is not always LLVM specific, but sometimes, and it certainly comes from my perspective working on LLVM. But on the other hand side, I will note if something is kind of LLVM specific whenever it comes up. So in a nutshell, LLVM is an open source compiler framework that has multiple front ends, multiple back ends, and kind of an intermediate representation in the middle end, and a lot of analyses and transformations there. It's an open community and open in a lot of other ways. So as an open source compiler, it is extensible and also fixable by whatever user you have. So it doesn't really matter if you're a company or if you're enthusiast or a government agency. If you have a problem, something is not right, or something should be better, you can kind of extend it or fix it yourself, which is kind of cool. It is portable, at least across modern commodity GPUs and CPUs. So it has backends for NVPTX for NVIDIA devices, AMD GCN for AMD devices, and there's more backends towards GPUs coming. And it supports a lot of kind of commodity CPUs. It has very good support for C++ and pretty good support for OpenMP, and then a lot of other of these kind of offloading languages, SQL, HIP, CUDA, and so on. It's kind of feature complete, I mean, eventually. And it gives you access to the coolest features early on, because a lot of the work in those standards towards those languages is actually prototyped as part of LLVM, which is why you can kind of try them out early on. Now, obviously, it's performing incorrect with a smiley face. That is the goal, but it's not always. It's usually not the case. We're just trying to. Okay. Then how does LLVM and especially the C++ front end Clang work? And it's like, you have to consider Clang is a front end for all C-like languages. That includes HIP, CUDA, SQL, and so on and so forth. All of that goes through Clang at the end of the day. And what Clang does, it takes a C file and it translates it into LLVM intermediate representation, LLVM IR. On that LLVM IR, you can then do optimizations. The tool, if you want to do that explicitly manually, is called opt, but Clang does pretty much what opt does as well. And then with LLC, you generate LLVM machine IR, And then you can actually optimize the machine IR as well. So a certain kind of optimization only happen on the machine IR, and then you generate machine code from that. If you want a longer introduction into LLVM, especially if you're interested in kind of starting to work with LLVM, I can recommend the YouTube link on the bottom here, partially because that was a tutorial I was involved in. But I think people liked it reasonably well. Okay, so that's enough here. Just to highlight, the part that I work on is usually this LLVM IR optimization level. So where we do mostly target independent optimization analysis on this LLVM intermediate representation. Let's take a look at OpenMP and LLVM, because that's kind of an interesting fact, and it actually kind of changed over the last few years a lot. So initially, if you think about OpenMP in a compiler, you think about the front end, in this case, Clang. It has an OpenMP parser, an OpenMP semantic analysis, and an OpenMP code generation. And you think that is OpenMP in a compiler, right? Like the front end that translates OpenMP, checks everything, and implements OpenMP. Maybe you also consider the runtime as part of OpenMP in a compiler, because the runtime is usually distributed as part of the compiler. So LLVM has libomp, and then GCC has libcomp, and other compilers have other OpenMP runtimes. But there's nowadays a lot more. For one, there's more runtimes. libomp is the classic host runtime for OpenMP, but we also have libomp target in all the plugins, which are responsible for target offloading, and then the plugins are responsible to talk to the device drivers. And then you have libomp target NVPTX, for example, which is actually executed on the device. So it's a runtime that we ship with the user code onto, let's say, a GPU. But that is not all. Nowadays, we're working very rapidly on the Fortran front end for LLVM, which is called Clang. So there we also will have an OpenMP parser, OpenMP SEMA, and OpenMP code generation. So now at this point, you might already see that there is kind of a duplication here, especially in the code generation part. You really don't want to duplicate that, because code generating OpenMP pragmas for C, C++, and for Fortran is pretty much the same task. So as part of the development of Clang, we're also kind of building this OpenMP IR builder, which is a front-end independent OpenMP LLVM IR generation that favors very simple and expressive LLVM IR. So in order to make it easier for analyses and optimization to work with that LLVM IR. And the fun part is it is not only usable for OpenMP frontends, like the Clang OpenMP frontend or the Clang OpenMP frontend, but if you had another language that has nothing to do with OpenMP, you could use this OpenMP IR builder to basically piggyback on all the OpenMP ecosystem and kind of translate your language parallelism into OpenMP parallelism without ever having a pragma. And then the kind of potentially most crucial part that was added in the last few years is OpenMP opt. That is an interprocedural optimization path as part of the LLVM core optimization pipeline that contains host and device optimizations. It is run by default with when you say O2 or 3, and there will be more ways to run it later on, even with O0 and O1. And really what it does OpenMP aware optimizations. So it knows about the semantics of OpenMP, and it exploits that to improve the performance of a program. And we'll get to that later. So OpenMP implementation and optimizations. Let's take a look what a compiler is supposed to do. On the left-hand side, you see an original program that is fairly simple. You have a variable y assigned to 7, and then you use the variable inside of a loop and after the loop. What you would expect the compiler to do if you turn on optimizations is to just replace y, you don't need it, and replace all uses with 7. That's going to happen with every compiler that you kind of pick up that is optimizing nowadays. Now, if we add OpenMP into the mix to parallelize our loop, because we heard that parallelization is kind of important, we should do that, you are in for a surprise with a lot of compilers. not only is the use of the Y inside of the OpenMP parallel 4 not replaced with 7 anymore, but depending on what compiler you pick up, the use after the parallel 4 might also not be replaced with 7. That's kind of a problem. So there are exceptions, and I don't want to judge all the compilers, but so far I'm not aware of one that I can access that replaces the Y inside the parallel loop by default. Now, you could ask, why is this important? I mean, replacing a Y with a 7, that doesn't seem to be kind of that big of a deal, right? So we did some experiments 2 years ago where we run a couple of benchmarks in 2 configurations. The base sequential version is just the benchmark without any OpenMP. It runs a single-threaded program, and we measure the time. The base parallel version is the same program, but the same benchmark, but OpenMP enabled, but then we execute it with a single thread. So both of them are executed by a single thread, but only the base sequential one was compiled as a single-threaded program, and the base parallel one was compiled as a parallel program, just executed sequentially. What you see here, Lulesh, with these inputs slowed down by like 3%, 3.5%, which is bad, but you could argue, I mean, you get parallelization and you would never run it sequentially, so you get your benefit later on. But then if you go and look at other programs, for example, breadth search, you already get a slowdown of 8%, which really doesn't sound great. And then obviously you kind of see where this game is going now. I'll just pick Pathfinder, and my slowdown is already 40%. So what I basically did by enabling OpenMP is I slowed down the sequential version of the program by 40%. In that, like, while you get your benefit of parallelization, sure, you actually slowed down a critical path by that amount. So there is more cost to pay. And those costs are almost entirely, if not entirely, because you miss out on compiler optimizations, as I showed before. Not necessarily we replace everything with 7, but compiler optimization nevertheless. And then there is my favorite example, which is SRAT version 2, which slows down by a factor of almost 2.5. So what you need more than 2 threads to even kind of be able to potentially recover that slowdown. So the first thing you did when parallelizing is really worsen the performance of your baseline, which is not really what we're looking for. Okay, so now we have this, but what should we do about it? First we go through, why is this coming from? And the answer is, it is due to the way OpenMP is implemented as part of the compiler toolchain. And let's take a look. And we're looking at a parallel 4 because that is kind of the poster child here. Everything else, like all the other pragmas and so on and so forth, are kind of implemented in a very similar way. Not all have the same complexity, but if you understand parallel 4 reasonably well, everything else kind of is the same. Okay, so we have this very simple input program in the top, a work sharing loop where out is in at 2 locations, okay? The sum of in at 2 locations. Now, what do we do? The first step, what happens in a compiler in the front end is that it will replace this parallel work sharing loop with a call into the runtime, into the OpenMP runtime. And that call will basically tell the OpenMP runtime that there is a parallel for loop. And it has the iteration space is from 0 to n. And the values that are needed to execute this body of the parallel for loop are n in and out. And then it will pass this body function, which is a parallel region outlined into a static function. So if you look at this body function, what it really is, it's just the body of the loop up there. And then it has a separate loop, which is going to iterate over the chunk. So each thread will basically execute this body function. And it will ask the OpenMP runtime, what is my chunk that I should execute? And then the OpenMP runtime will provide this lower bound and this upper bound, and then this thread will execute all iterations of that chunk. That is more or less what happens, at least in Clang, and generally speaking also in a lot, if not all other compilers. This is a little bit simplified, but the gist is there. Now, if you look at this parallel for call that goes into the runtime, and if you look at this body function, you can kind of see that there's an obvious connection. So the body function is passed to the runtime, and all the arguments of the body function, except the thread ID, are also passed to the runtime. So we kind of tell the runtime what to call and what the arguments are, because we only know that at this point, at this point where we generate this runtime call, but the runtime doesn't really know that. So the runtime is just going to kind of take this function pointer and call it with the arguments that were passed. Now, one thing to notice here is that we take the address of all the arguments. So n in the above code was an integer. And now what we actually pass is the address of n, which is an int pointer. And the same holds for in and out, which were floating pointers in the above example. And now we pass their addresses, which are floating pointers. And what that means is, if you look at the code inside of body function, is that we have to first dereference n in and out before we actually get to the value we're looking for. So we basically introduced one level of indirection here. And that should kind of concern you, because the level of indirection is always bad for performance. So what happened? What happened is that if you pass, depending on how you share a variable, the value is passed or communicated through the runtime with a different type. So by default, you have in a parallel forward, variables are shared. And if you have a variable of type T that is shared into a parallel region, it will actually be passed as T pointer. So the address of the variable is passed. Same for last private. Why is that? Because in both cases, inside the parallel region, we might modify the variable. And for the modification to be visible after the parallel region, we have to provide a way to write in the original storage. And the way that is usually done is just provide the pointer to the original storage. But this indirection that we introduced here causes us to causes an indirection everywhere in the parallel region. So passing something as shared or last private is usually bad. If you pass something as first private, however, we'll make a copy of it. So if you pass a variable of type T as first private, we'll pass it as type T. So that is kind of what you want to do. If you pass something as private, we're actually not communicating anything. We're just allocating a new variable inside the scope. So that's also very good. And now a rule: you should use default first private pretty much always. If that is not implemented by your compiler yet, you could use default none and then first private everything, all the variables explicitly. I say almost because there is one more or less exception here, or two. One is arrays that live on your stack, which are, at least in the codes that I see, not that common, but those ones are exceptions. And the other exceptions are values that you really use to communicate between threads. So, but in order to determine if that is the case, you can go by this idea. If you have a value and it's not a reduction, and it is not, and you don't use any synchronization primitives to guard the accesses to that value, you can use first private. That should almost always work. And I mean, you can try it out, and if it doesn't work, it should be fairly obvious that it doesn't work. Okay, so that was kind of a quick guide on what kind of data sharing to use. Let's go back to our example. So this is the same slide I showed before. You see the weak connection between the parallel runtime call where we pass all the values, and then you see the how they end up in the parallel function as arguments. Now, if you want to optimize this, because right now this will not be optimized. So because we go basically through the runtime, through a function we don't know, the compiler has no chance of optimizing this. The compiler doesn't know what parallel for, like the runtime call parallel for does. What people proposed is, let's make it explicit. Let's kind of have an intermediate IR that is parallel. So we have in the compiler, we represent this as a parallel for, and then we just call this outline function, and then it is really explicit what is happening here, and you get optimization. And if I would build a compiler from scratch, this is what I probably would do. However, if you take a compiler that is existing, that has a lot of optimizations that assume sequential semantics of the control flow graph and other things, this is going to be like introduce very subtle and sometimes not so subtle errors. So doing this and hoping it will work without a substantial amount of changes is illusionary. So we kind of decided against this, and instead, let's go back to the picture we had. Instead, let's take a look again what we have here. You see that we know, like as with our domain knowledge, that the parallel for runtime call is going to call the body function and is going to pass n in and out. We know that. Why don't we tell that the compiler, such that the compiler can do interprocedural optimization here? Because it now knows that the only thing that happens here is that body function is called with those arguments. So what LLVM, what we actually do now is we model this transitive call. So this call that happens inside the runtime of the body function with those arguments. Now the question mark here basically says there are some arguments that we don't know what will be passed. So this is kind of an partially known call site. So we don't really know what everything is passed, but we know some of the things. And now LLVM is going to perform interprocedural optimization across this transitive call site that we kind of pretended to exist. And we do this by introducing domain knowledge about this runtime call. And we get to that a little bit later, because it's not only that runtime call that we introduce domain knowledge for. Okay, so we did some experiments back in 2018 when we started this and prototyped this. So we had a base version, which is just plain 03. And then we used two interprocedural optimizations that exist in LLVM, which is attribute propagation and argument promotion. And we kind of taught them about these transitive call sites. So we explicitly made them aware of these transitive call sites. But we used the same logic for the interprocedural optimization. And then we run the experiment again. And now this is the loot benchmark. And you see by the base S in the very left, that is what we had before, base sequential. And then the second from the left is base parallel. So those are the two that I showed before. And it kind of slowed down 25% if you run it with OpenMP enabled in a single thread. And then you see if you, on the very far right, if you enable both of those interprocedural optimizations with the knowledge about these transitive calls, what you get is basically the same performance as base sequential within the noise. So really adding the domain knowledge and making sure that the compiler can do optimization across those outline functions is what you need to get your performance back that you kind of lost by parallelizing. And then let's go to my SRAT example that was really bad before, 140% slowdown. And again, if you combine both of those, or actually if you combine both of those analysis, you get exactly the same performance as you had in the base version. So teaching those interprocedural optimizations about these transitive call sites makes the difference. There's a couple of other things you want to do that didn't turn out in these benchmarks, but the main idea here is that even if you do early outlining, even if you have the indirection through the runtime, which is a good thing because it prevents you from accidentally miscompiling, you can do optimization through selective modeling of the runtime behavior. Okay, let's switch gears a little bit. so far mostly about like parallelism optimizations, but they were not really OpenMP aware. Like we can do the same things for pthreads or anything else. So it wasn't really about OpenMP. But we also have added, or we have started to add OpenMP aware optimizations into the compiler, in this case LLVM. So what we really want to do is we want to have an OpenMP aware compiler. In the long run, we want to have a parallelism aware compiler, but OpenMP is a good first step, and then generalize from there. Now, remember in the very beginning, I showed you the different parts of OpenMP and LLVM, and one of those parts was this OpenMP opt path, which is this interprocedural path. And by now you might have realized why this path is interprocedural, because as part of the OpenMP lowering, we outline stuff. So we have to be interprocedural to do reasoning between the location where the parallel was and the parallel body that we outlined. And the OpenMP opt contains host and device optimizations, and it runs by default. Now, what can it do? It knows about the OpenMP API, so get thread num and other calls. And it also knows about most of the API calls, and we're teaching more and more as we need them. And it knows about the internal OpenMP runtime calls that we use to implement OpenMP. And one thing it, for example, does, it annotates those calls with their potential effects. So it knows that pretty much none of these calls can throw an exception. Before, those calls were pure optimization barriers. So when the compiler saw one of those calls, which was going to call into an unknown runtime, it had to assume the worst, that the program might exit and all visible state is changed, or there is an exception thrown. But now we actually embed this domain knowledge, and now the potential effects of these runtime calls is known to the rest of the LLVM compiler, and therefore more optimization can happen. We also perform very high-level optimizations that are kind of not part of any other LLVM path. For example, parallel region merging. It's not like that is, it is a thing that you have to have awareness of what a parallel region is, what it means to merge them, what you have to verify that that is sound, and how to modify the code to actually make it happen. And when, for example, what do you do with sequential code that is in between parallel regions? Can you execute it redundantly, or do you have to guard it and execute it single-threaded and have to kind of introduce barriers and propagate the results among all the threads and so on and so forth? So all of this reasoning is kind of on a high level, because you have to argue about things that are not explicit in the IR. It also has a lot of GPU-specific optimizations that run late in the optimization pipeline, and we're going to see some of them later on. Now, the last thing is, there are, like, historically, it was Clang, the front end, that did optimizations in quotes. So because we didn't have OpenMP opt, all of the kind of tricks that we wanted to do when we compiled OpenMP had to happen in the front end. And that had a couple of not so nice side effects. One of them is that it was very syntax driven. That is, if you had two programs that were equivalent, but the syntax was a little different between them, one of them might have been a lot faster than the other. And it was not really clear to anyone why, that didn't really know what Clang was doing. And there was so far no way for to ask Clang what it was doing anyway. So it was kind of a black box that sometimes performed well and sometimes didn't. And it also introduced a lot of complexity, which complexity leads to errors. So what we are already doing for now years is we are removing a lot of the smarts from Clang and putting them into a middle end. It has a lot of benefits, one of which is also all of these optimizations will also trigger for Clang when you have the fortran front end. And the middle end is where all the other optimizations are done. So keep the front end simple and emit code that can be analyzed and optimized later on. That's the thing that we're doing here. Okay, now talking about you don't really know what happened, and Clang either performed well or gave you code that was slow. One of the things we do with the OpenMP opt is we really put a lot of effort in adding optimization remarks, such that if you run this program here, you want to know, the LLVM compiler will tell you that it actually merged those two runtime calls on getThreadLimit into one. So if you run this and you say rpath equals OpenMP opt, which is the remarks interface from Clang, it will tell you that it moved one of those calls into like a different position, and then it deduplicated the calls. So instead of calling the function twice, it just calls it once and reuses the result, because OpenMP opt is aware that the result of that function will not change in this scope. Then there's also, like, we have also remarks for target scheduling. So if you have code that is offloaded to a GPU, there is a lot of things that we want to do with regards to optimizations that are important for performance and register utilization. And those things emit a lot of remarks. They tell you if it worked, and what didn't. So if you run this in LLVM 12, you get a wall of text. It's kind of, it wasn't great, and we're working on it to make it better. I'll explain what the wall of text kind of means, or basically what optimization we're performing a little bit later. So let's skip this for now. Now, in addition to this compile time information, we're also working very hard to embed better runtime information, because at the end of the day, if the compiler is a black box and the runtime is a black box, people are unhappy because they want to know what is going on. And I understand that, because they want to know why things are slow or fast, what they did right or wrong, what the compiler decided, and where they have to help. So I would encourage everyone to use optimization remarks. They exist not only in LLVM Clang, but they also exist in other compilers. For the LLVM Clang case, we have remark explanation, examples, FAQs that we add over time to the OpenMP LLVM org/docs. So the documentation page there is the relevant new web page that you should kind of visit and potentially revisit over time, because it's kind of new, but it already contains a lot of interesting information, especially about the environment flags that you can use to talk to the runtime. And one of the most important ones here is libom target info. You can use that to let the runtime, and I mean the generic fast release runtime, tell you what it did and why it did things. And it also helps you a lot to debug potential errors, because it gives you information about what pointers are mapped, when is data copied, how are kernels started, and so on and so forth. So there's quite a bit of things that you can get from the runtime nowadays, even in release mode. So I would encourage everyone to take a look at those. Okay, let's talk a little bit about OpenMP offloading. We kind of alluded to this. So when you have, by default, you have the host OpenMP compilation, which takes the C input, preprocessor, compiler, backend, assembler, linker. That's your usual compilation pipeline. Now with device offloading, we take the same input again and compile it again. With another, like in LLVM, we actually run a second preprocessor run. We run a second compiler, and then we have kind of an offload step that takes information from the host compilation as part of the device compilation. And this is kind of crucial here, but I'm not going to go into much detail. Then we go through the assembler, the object file linker, same as before. This time we just have a different target. In this case, if you see in the top, the target that we compile for is MVPDX64. So once we link and have an image, what we do is we invoke an additional step that embeds that image into the image of the host. Because at the end of the day, what you want is a single object file. So you want all your tooling, all your build setup to work even if you do offloading. So we have to only generate a single file, and we have to make everything work as it did work before, but now there is 2 targets or even more potentially involved. OpenMP offloading has quite a few tricky bits, and I'm going to talk about 2 or 3 of them now. One of them is kind of sketched here. So it's the use of math functions, but it's not only math. It could be any system header or any library at the end of the day. So if you have this function called science here that is inside of a begin declare target, it uses a math function, sign bit f. So to determine what the sign of the float f is. Now, the crucial part is science, this function, can be called from the host and the device. So there have to be 2 versions of that function, one that is called that is available on the host, one that is available on the device. This would all be fine if math.h would be relatively the same. But if you open up your math.h and then go through all the other include files that it potentially has, you potentially, and depending on your version, may or may not end up at code like this. And the important part here is that it has this if-def, where it checks if SSE2 is available and used for math, and then it uses this inline assembly instruction that kind of only works on x86. Now, if you compile this for a CUDA GPU, that inline assembly will not work. I mean, it will not compile. So you basically have 2 different versions of this function for the host and the device. And you have to be kind of careful on what to do. And there is potentially not, and this is only one of the problems. The other problem is GPUs actually don't come with a math.h. They don't even come with a libm, like the math library. And that is a real problem now, because now if something in math.h on your host is not defined, but only declared, and then the implementation is inside of libm, what are you going to do? You still want people to be able to use those functions. So what LLVM Clang does, it provides a math.h wrapper, among other things. It's not only math, but one thing that it provides is a math.h wrapper that defines a lot of the math functions. And then it uses the declare variant feature to overload them. So if you call sign bit f on the device, you actually get the function that we have in this wrapper, which then is implemented through means, in this case for NVIDIA built-ins. And then the same trick applies to all other GPUs and so on and so forth. Okay, so then the other tricky bit is linking. As I said before, you want all your build system and everything to work as it did before, but that is actually really hard to do, and I get sad when I think about it, so we're not going to talk about it today. Instead, we're going to talk about OpenMP offloading versus kernel languages, and I have to kind of speed up a little bit. So in the top, you see how you start a kernel in one of the popular kernel languages, where the func is the function that you start. You start it with 1 block and 4 threads in the arguments. On the bottom, you see pretty much the same code, except that you also execute this A and this B in between, before and after the func function. If you look at how that translates visually, so for the upper part, you have a block and you start 4 threads, and then all of the threads execute func, and that is it. On the lower part, conceptually, you start 1 thread, and then you execute A, and then you start the rest of the threads, the other 3, and all of them execute func. And then the 1 thread executes B, and that's it. However, this is not how GPUs work. The parts that are highlighted in blue here, they can't exist. So you cannot just kind of start the threads when you need them. They are started at the very beginning and they exist. And now you have to do something with them. So what happens in the runtime is they execute something else. So they execute something blue while they wait to be told what function they're supposed to execute for real. Now, in LLVM speak, the upper one is called SPMD mode, when everyone executes the same stuff. And the lower one is called generic mode, when there's 1 thread that executes the user code, and then the other threads, the workers, execute only the parallel regions. How is this done? Before we go to that, you might think, why don't we just use conditionals? We say every thread starts at the beginning, and we execute this A part and this B part only by the main thread. So we use a conditional and say, oh, A is only executed by the first thread. Then we wait, we have a barrier, so everyone is on the same page. Then everyone executes func, we barrier again, and then only the first thread executes B. This is a nice idea, and this optimization actually is about to happen inside of LLVM if it's legal, but it's unfortunately not always legal. So if the green part, for example, contains an unparallel, your behavior will change. And not only will it change, it will probably be not what the user wanted, because now this kernel 2 is not executed in parallel at all, because all the threads are busy kind of waiting at the barrier. And if you have a barrier inside of this yellow part, you even have a bigger problem, because now not every thread in your team will actually reach that barrier. And that is kind of bad. So this optimization, usually called SPMization, is coming soon for the cases that we can prove everything is legal, and we're going to make it stronger for LLVM 13. So watch out for that. But how is it really done right now? How is generic mode implemented? There is this one thread, the main thread, that actually executes the green block, then func, and then the yellow block, okay? The other threads are executing something else, and they're waiting in this bubble. And then at the point when we hit a parallel region, before and after, the main thread is going to tell the other threads what the parallel region is that it just encountered. So it tells them it's the gray block. And then the others are able to execute the gray block and hit another bubble where they wait. Then they tell the main thread they are done. So everyone is done executing func. And then the main thread can continue while the worker threads go back to the initial bubble and wait. The right part is usually referred to as the worker state machine. This is how LLVM executes generic mode. Now, you have to see that this gray box here is actually a function pointer that represents this parallel region, because we have to somehow identify a parallel region between the main thread and the workers. And the function pointer we outlined the parallel region into is not only an obvious choice, but it's pretty much the only choice if it's pretty much the only choice in a generic setting. Now, the problem with passing function pointers on a GPU is that you have indirect calls and spurious call edges, which increase your register count quite a bit. So what you really want to do is you want to try to avoid the function pointer use and use some other kind of identification, some other kind of IDs that are not function pointers. Let's take a look at that optimization. Yes. So this on the left is how the code really looks simplified on the GPU. So the kernel is executed, and then the threads are split into workers and the main thread. The workers wait in the state machine, this while on loop. They wait for a new parallel region to arrive, they execute it, and they signal that they're done. The main thread is going to tell the workers, here's the function pointer of the parallel region, and then everyone executes it. And then the main thread waits for the workers. So this is what we discussed before already. And what we can do with this is we can replace the function pointer by a unique ID that represents the function. So we create a character, for example, in static character in the global space, and we use that address to refer to the function. So now we never take the address of the par function, and we never pass a function pointer. That actually is a really big improvement over the code before. This works except if the parallel region is accessible from the outside. So if a kernel that we might not know could access that parallel region, because now how is the kernel that we don't see going to know about this ID that we introduce or that we want to introduce? It isn't. So we still have to pass this function pointer. If we had like an OpenMP assumes that says there are no external callers to this function, we could still do the trick. And this is kind of where we are going right now. We're going to emit remarks that tell you why things didn't work out. And we're going to ask the user to provide these additional information, for example, through LLVM, through OpenMP assumes that were introduced in 5.1. And then users get better performance. Okay, so LLVM 13 will know about this and a couple of other things in this area. Let's skip ahead, but don't forget to use remarks because that will also tell you about missed opportunities. Let's skip ahead let's do OpenMP got wrong, but we skip ahead over the rest. Anything that retroactively changes code, any directive, is a bad idea. So here you see the static int x, and you see that we use the alignment of x right away, and then we kind of use x to inside of a function, and after all of this, we change the way x is allocated and what the alignment of x is, and that's kind of bad. And there's not only that, there's other examples. This is just one of them. So anything that retroactively changes something is a bad idea. It can be implemented, but it's usually a hassle, and the part I'm not really sure we would do that. And then there's a fixation on syntactic nesting. So if you have an OMP target with an atomic update inside, that's fine. If you have an OMP target teams with an atomic update inside, that's not fine. But if you then outline this code into a function foo, that's fine again. So it's really like not only about atomic accesses in teams regions, it's more about the idea that we have to kind of define everything with regard to syntactic nesting that I think is inherently wrong and makes things very much awkward half the time. There's a lot of things that OpenMP got right, and the device abstraction is one of them. So we see that you can have one GPU that would be your device 1, second GPU that would be your device 0 and then device 1. But the device abstraction allows you to do fun things. For example, add 9 more GPUs in the cloud and pretend they are local. So GPU 2 to GPU 10 are now shown to you as if they were local in your computer, but they actually sit somewhere else. And with LLVM 12, you actually have the ability to do exactly this. So you can make remote GPUs look as if they were local. And then there is the other use case. You have your own multi-core, and you can offload to the CPU device. But what you can do in LLVM 13 is you're going to be able to offload to a virtual GPU that runs on your host, but for all intents and purposes, kind of looks and feels like a GPU. The programming model, the device runtime, the compilation path, everything kind of is the same as for a GPU, except that it runs on the host, which allows you to do debugging much easier. Okay. Why is this all possible? This is possible because there is the OpenMP and application world, and then at some point there is the device abstraction world. And there is a fairly nice clean cut in between that allows us to just add different devices and expose them to the OpenMP world, even if like they have the same hardware backing or are not hardware at all or are hardware somewhere else. So this kind of abstraction layer is really nice and really helpful to develop a lot of cool tools. Okay, I'm going to show the what's next slide in the end because we're running out of time, and I was hoping to see if there are any questions. So my final thoughts. One thing that I see a lot in academia especially is the idea that a work sharing loop is a parallel loop. So on the left, you have a work sharing loop on parallel 4. On the right, you have what OpenMP now actually offers you as a real parallel loop. That is a loop that is that doesn't have loop carried dependencies. And you use the order concurrent. And they're not the same. For one, if the schedule that is chosen for the parallel work sharing loop has a chunk size that is bigger than the loop iteration count, that loop is executed sequentially. So there is no parallelism at all. Similarly, if somebody sets the number of threads before that loop is executed to 1, again, no parallelism at all. So pretending an unparalleled for loop is a parallel loop can be dangerous if you use the parallelism to do optimizations. So without OpenMP assumptions, that is not really doable. but that is why we have introduced the OpenMP assumptions to allow the user to guarantee all of these nasty corner cases won't happen. Okay, now 10 minutes to go, and I'm happy to answer any questions in case there are some. Let me take a look. I think there are a few. Okay, one question is, I use standard libraries of C++ 14, C++ 17, and to some extent C++ 20 to write parallel applications. Does C++ standard libraries have inherent limitations when it comes to parallelism? I mean, the limitations with regards to the outlining and preventing optimizations are not OpenMP specific. Pretty much every parallel programming language is implemented in the same way if you look at the bottommost layer. So all of them are suffer the same fate. The abstractions that we use to bridge that gap, this transitive call types, for example, apply to all of them though. Like it applies to pthread create, which is the underlying concepts on all of them. And with this transitive call types and then interprocedural optimization, you get a lot of the missed opportunity, missed parallelization back. So C++ parallelism is not inherently different from any other one. So OpenMP is also not inherently different from OpenACC or TBA. Like all TBA, it's all conceptually very similar. Okay, another question we have here. The use of first private as a default data sharing method. Well, it reduces indirect memory accesses, but wouldn't it also add memory storage overhead due to storing multiple copies of the data item, and also might affect consistency among threads if the variable is modified by other threads? I mean, absolutely. If you have, especially the later part, if you actually modify a variable by different threads and that modification has to be visible, then you need shared. However, if you do that, that only works if you do explicit synchronization. That means that there are some like critical, some lock, some form of synchronization has to be present. And if you look at your program and there is none such synchronization there, you actually don't modify stuff that has to be shared. You might modify memory that is kind of accessible by all of them, but not the variable itself. For example, the pointer that says where the memory is. And with regards to the overhead in storage, most, like with the exception of stack arrays, everything else is small. Like we're talking, like all of the values usually fit in registers, right? Like there might be exceptions if you have huge structs that you don't want to pass by value. But other than that, I would recommend first private all the time. Talking about first private, is the use of first private also recommended for OpenMP offloading? After once task got introduced, we actually, like the OpenMP standard got it right and started to use first private for tasks as a default. So OpenMP target creates a task, and that task will by default take all the variables as first private. So the entire discussion about you should use default first private really only applies to a parallel. Because that is historically sharing variables by default is shared, and that is the problem. But the task construct and the target construct and so on, they actually share variables as first private by default, so you're good on that end. Very nice. I wonder if multiple back-to-back barriers can be detected and optimized into a single barrier. Yes and no. So this is fairly, I mean, it a little bit depends. So if you can prove that all of your threads actually make those barriers, yes. On the GPU, for example, that is in the scheme that I showed earlier with the state machine, there are literally 2 consecutive barriers that are executed by the main thread in reality, but you cannot merge them because they're like barriers that are only executed by a subset of threads and are consecutive cannot be merged. If all the threads execute those barriers, then you can kind of replace one of them. We had a prototype of a barrier elimination, and that is like, given our initial experiments 2 years ago, that becomes useful if you actually make implicit barriers explicit. And that happens if you merge parallel regions. As soon as you merge a parallel region with another one, or then the in-between, like the end of the first parallel region has an implicit barrier, that one has to become explicit. And once you start doing these, like having the barriers explicitly, that is where you might really benefit from barrier elimination. That said, it really, like, I haven't really found a case where without parallel region merging, barrier elimination is helpful that much. And implicit barriers removing is a tricky business to begin with. I might be wrong about that because I haven't really looked at implicit barrier removing really. Okay, use cases for the vGPU in LLVM 13. Right now, if you do offloading, you offload and you want to debug your offloading, or you don't have a GPU available and you want to test it, you can offload to the host, which is your CPU. However, if you do that, at least in Clang, the code generation part, the device runtime that is executed, pretty much everything is different than if you offload to a GPU. It goes through a couple of similar runtime calls to do some of the communication, but almost like the majority of things in the entire path between compilation and execution is different if you offload to the host or if you offload to a GPU. With the vGPU, we bridge that gap. So if you offload to a virtual GPU, it's pretty much the same code generation. It's pretty much the same device runtime, everything as if you would have offloaded to a physical GPU, which allows you to debug your code that is very close to what would run on a GPU, but you can debug it on the host. So you can attach a debugger, you can look at you can use GDB directly, and so on and so forth. And it is executed, or you can use a thread sanitizer for all that matters. But it's executed with the same model of execution as it would have been on the GPU. Do you think postponing the outline transformation will be helpful applying traditional loop level optimizations in LLVM? The short answer is no, because LLVM doesn't have strong loop optimizations. The longer answer is yes, there is a potential to apply, there is a potential to apply loop level optimizations if you do later outline. However, you have to see that it is much more complex to do loop level optimizations across a loop of one of which is a work sharing or parallel loop. I mean, that requires the loop transformation to know about this, because you want to be aware what it means. You want to preserve the parallelism and so on and so forth. So just thinking, oh, I could just use interchange across a parallel loop, it's not going to work the way you want it. And that means that it might not be the only way to just do late outlining and therefore kind of be able to reuse, because you can't actually reuse. Maybe there is another way. That said, the abstraction that we use right now with the transitive calls is not necessarily the solution either, because that works well for classic scalar optimizations, but not for loop level transformations. What I think for loop level transformations people should do is should use the loop level pragmas that OpenMP started to introduce in 5.1, because they are applied early and they are aware of the OpenMP other pragmas like work sharing and parallel, and they kind of do the same thing. It's not automatic with regards to determining what to do, but then you can use an auto-tuner if you want, and people are working on that. Okay, when you mention retroactive syntax, it reminds me of pragma thread private list. is the OpenMP spec changing that one as well? I don't know if the OpenMP spec is going to change the things that I think are broken. I hope so, but I don't know. I can't really tell you. Are there conventions to avoid using a target parallel region like overloaded operators or weird collections? Need the application developers to be GPU aware when writing code? One thing that will just not work is if you use containers or something that are partially defined inside of the standard library. So if you don't have the source code in the header, you would need the standard library for the GPU, which we right now don't have, at least not on all devices. And we really, like in LLVM, we don't really link anything in there. So that is a problem. If you use the header only parts of these things, they should work. How well they work is a little bit of a question. Schedule concurrent. Last slide. What is it good for? Oh yeah, it's order concurrent, and that basically is saying that is the real parallel loop where you say this loop doesn't have loop carry dependencies, and it actually has a couple of other restrictions that come with it, not all of which I think are even necessary, but it really says this is a parallel loop that doesn't have loop carry dependencies. You can optimize it under the assumption that, for example, accesses in different iterations do not map to the same memory. They cannot. So that for example, based on that, you can potentially prove that two arrays are not aliasing, and you can use that. For traditional work sharing loops, that is not true, because with environment variables and these runtime calls like the setters and so on, you might actually make the work sharing loop sequential, and then these arrays could overlap all they want and it would be legal. And if you assume they are not, you might miscompile the code. So I'm trying to avoid that. What kind of issues could be addressed by making reasoning more semantic aware over syntax dependent? The issues like the one I showed, where you have to manually outline a little bit of code just to make it work, and it wouldn't work as expected, and it works. It has perfectly fine semantics. It's the question. It is just that the compiler says this is not allowed. But if you outline it into a function, everything is fine. So that kind of hoops that you have to go through seem utterly unhelpful. And there's more than just that one. And a couple of those are just kind of the standard forgot to remove restrictions over time, and I'm part of the standard committee, so I'm to blame as well. Don't get me wrong, I'm not trying to like shift the burden. Like I screwed up defining stuff, my fair share. But that is kind of what I see is problematic. And if you define stuff more semantically, you're able to also compose transformation and better. Which OpenMP feature do you think should be deprecated in the next standards? That's a good question. Sections for one, and this do across seems to be something that I'm not sure if anyone uses that. I haven't seen it yet. There are more, but I want to be more careful what I say next. So I'm going to stop at that with those two. There's also a couple of clauses or options that I would deprecate and remove. What is the current status of utilizing user-provided assumes in LLVM? What kind of assumptions can a user provide, and how are they utilized? We really use only one assumption, and that is the assumption that no OpenMP or no OpenMP API. So as part of this GPU state machine optimization, we try to get rid of this fallback call that calls the function pointer that was passed. So if we have this ID transformations, hey, try not to use function pointers. But there's always this call that says, if I encounter a parallel region that I didn't see before, that, for example, in a different translation unit or so, and that in that different translation unit, there is a parallel region that I encounter. I have to kind of pass that function pointer of that parallel region to my workers so that they can actually execute that function in parallel. Now, this is a problem because you have this indirect function call left over. But if you actually never use this feature such that you have a parallel region in a separate translation unit, but you have calls that we cannot analyze, you can annotate them with assumes no OpenMP or assumes no OpenMP API calls. And then we will know that these calls call into a separate translation unit that we cannot analyze, but you promised us that they will not have any OpenMP parallel regions in them. So we don't need to keep this fallback function pointer call around. And just removing the indirect call is potentially a big benefit. So that is the only one we use right now. There are others that we are going to use, but they only make sense if you also have remarks that tell people what is happening, why did we miss something, and tell people to use them in a proper way, because guessing what assumptions to use is not helpful. Okay, that was all the questions. And we're reasonably over time, so I guess we should end this.
Great. Thank you so much, Johannes, and thank you all for your time today. We hope you enjoyed the webinar. A recording of this presentation along with the slides will be available on the OpenMP website. We will send you a direct link in a follow-up email. Also, as you leave the webinar, please take a moment to fill out the survey that pops up. Your feedback is important to us to help us improve these presentations. And we'd also love to hear if there's any other OpenMP related topics you may be interested in. Hope everyone has a great day. Thank you.